Hello again. In this video, we're going to begin talking about the material from section 4.2, which is about the mean value theorem. Now, before we talk about the mean value theorem, we need to talk about a preliminary theorem known as Rolle's theorem. So here's what Rolle's theorem says. Let f be a continuous function on a closed interval from a to b, and differentiable on the open interval from a to b, with f of a equal to f of b. Then there's at least one point c in the open interval from a to b, such that f prime of c is equal to 0. Let me show you why this is true graphically. So let's take a function that satisfies all three of the conditions of this theorem. So the first condition is that the function must be continuous on a closed interval from a to b. So you can see in this example, this function is continuous on the closed interval from a to b. So that condition is satisfied. The second condition is that the function must be differentiable on the open interval from a to b. Now, differentiability means that the derivative exists. And so this means the derivative must exist at every point in between a and b. If you look at this, you can draw a tangent line at this point, and the slope of that tangent line exists, right? It's some number. And that's true for every single point in the interior between a and b. That means the derivative exists at every single point in the interior between a and b. Therefore, f is differentiable on the open interval from a to b. Okay, the last condition that we need is we need f of a to equal f of b. In other words, the y value at the left endpoint, f of a, needs to be equal to the y value at the right endpoint, f of b. And you can see in this case, they're both the same y value. All right, so this particular graph satisfies all of the conditions of Rolle's theorem. And so the conclusion says there must be at least one point c in the open interval from a to b such that f prime of c is equal to 0. And you can see that it's at this point right here. First of all, c is in the interior between a and b, right? And you can see that the derivative at c is actually equal to 0 because the slope of that tangent line at this particular point is 0. Okay, so that gives you kind of a graphical sense of why this theorem is true. But I want to go ahead and show you the proof of the theorem. So let's go over the proof. Okay, when you prove any theorem, the first thing you do is you assume that all the conditions are satisfied. So we're going to assume that we have a function that's continuous on a closed interval from a to b, and that it's also differentiable on the open interval from a to b, with f of a equal to f of b. So we're assuming that we have a function that satisfies all three of those conditions. And then what we're going to have to show is that there's at least one point c in the open interval from a to b such that f prime of c is equal to 0. Okay, so let's prove it. All right, so the first step is we're assuming all three of those conditions are satisfied. But let's look at this first condition. The first condition says that f is continuous on the closed interval from a to b. By the extreme value theorem, we know that if a function is continuous on the closed interval from a to b, that the function must attain its absolute maximum and absolute minimum values somewhere on the closed interval from a to b. And that's by the extreme value theorem. We talked about that in a previous video. The condition of the extreme value theorem is that f is continuous on the closed interval from a to b, and the conclusion is that if that happens, then the function must attain its absolute maximum and minimum values on the closed interval from a to b. Okay, so we know that. But we also know that absolute maximums and absolute minimums can only occur in one of two locations. They either occur at the endpoints of the domain of the function or the interval that you're working with. In this case, the endpoints of this interval here, which would be the left endpoint is A and the right endpoint is B, or the absolute maximum and minimum value can occur at a critical point in the interior in between A and B. Okay, so just keep that in mind. We We know that has to be true. So to prove this theorem, we're going to break it up into two cases. The first case is the case where f attains both its absolute maximum and minimum values at the endpoints. So without loss of generality, let's assume that the left endpoint is the absolute minimum, or the location of the absolute minimum. So f of a is the absolute minimum. And let's assume that f of b is the absolute maximum. Now you could switch those and the proof will still hold, okay? So that's what I mean by without loss of generality. So let's say f of a is the absolute minimum and f of b is the absolute maximum. But we know that f of a is equal to f of b, right? That's one of the conditions of the theorem. So let's start at a. We know f of a is the absolute minimum. If the function were to go down from a, then f of a would no longer be the absolute minimum. So it can't go down from a. Okay, let's start at a again and go up. Maybe the function goes up from a. Well, if the function goes up from a, then f of b can no longer be the absolute maximum. So the only possible thing that the function could do starting at a is to stay constant. And it must stay constant starting at a and going all the way across the interval until it gets to b. In other words, we have a constant function on the closed interval from a to b. And since we have a constant function, the derivative of a constant function is 0. So for every x value in the open interval from a to b, we know the derivative of that x value has to be 0, since the function is constant from a to b. And that proves the theorem because we found a point C somewhere in between a and b where the derivative is equal to 0. So that proves the first case. Right, the case where the absolute maximum and minimum values occur at the endpoints. Now the other case that we need to look at is, let's assume one of the absolute extreme values, right, either the absolute max or the absolute minimum, does not occur at an endpoint. Okay, that would mean that the function must attain its absolute extreme value at some interior point between a and b. In fact, it must be at a critical point in the interior between a and b. In fact, even more than that, it must be at a turning point. Right? It must be at a local maximum or a local minimum point. Let's call it C, somewhere on the open interval from a to b. Now remember, if you have a local minimum or a local maximum, there was a theorem that said if f has a local minimum or a local maximum at some point C, then either the derivative at C is either 0 or the derivative at C does not exist. But we can eliminate the case that the derivative at C does not exist, because one of the conditions here is that f is differentiable on the open interval from a to b, so that couldn't be the case. So that forces the derivative at c to equal 0. And therefore, we did find some point C in the open interval from a to b where f prime of c is equal to 0. And the conclusion of the theorem does hold in that case. Okay, so that proves Rolle's theorem, right? We've proved both cases that are possible. Okay, I guess the last thing I want to talk about in this video is, why does Rolle's theorem require continuity? And we can look at it and why does it require differentiability for that matter? So there's a couple examples we can look at to check this. Let's suppose that we had a function that wasn't continuous on the closed interval from a to b. So there's some discontinuity in between right here. Well, you can see that there's no point in between where the derivative would be 0, right? The slope of the tangent line is not 0 at any point here. So you can see that the conclusion does not hold. We do need continuity on the closed interval. So that's kind of a counterexample for continuity. Why do we need differentiability, right? That's another condition that this theorem has. F must be differentiable on the open interval from a to b. So let's suppose there's some point where it's not differentiable in between a and b. So right here. And you can see that's not differentiable because it comes to a sharp point. So it's not differentiable right here. Well, you can see that there's no point in between a and b where the derivative is 0. The slope of these tangent lines are never 0. And the slope of the tangent line right here is undefined because you have a vertical tangent line right at that point. So there's no point at which the derivative is 0 in between a and b. And therefore, the conclusion would not hold in that case. So we need differentiability on the open interval from a to b for this theorem to hold, as well as continuity on the closed interval from a to b. Okay, so next time I'm going to do an example where we actually apply Rolle's theorem. Okay, until then, I hope you found this video helpful. Thank you for watching. Bye-bye.